Welcome MA 103 students. This video AI corresponds to the lesson entitled Modeling with Linear DDS. In this video, we will focus on the first lesson objective listed here, model situations and solve problems involving linear DDS models. This is the second video in a series and builds upon the transform step in the first in order to both solve and interpret the problem concerning the colonization of the moon. In the first video, we were able to transform this problem using the transform step of the USMA mathematical modeling process and including the three essential elements to create a mathematical model. And that model was P naught equals 0 and P sub n equals 1.04, P sub n minus 1 plus 75. We can now use this mathematical model to solve and answer the question, what would the population of the colony be after 20 years? So what we're really trying to find is P sub 20 using this mathematical model. We'd like to iterate in order to find P sub 20, and let's turn to Microsoft Excel to assist us with this. Let's set up our Excel spreadsheet. We know there are two things that we want to keep track of, and that is our time index n in years, as well as our P sub n, which represents the number of colonists on the moon after n years. And we know we want to go to 20, so let's fill in 0 to 20 in our first column. And then to fill in P sub n, the column for P sub n, let's define the parameters for our model separately, and we can reference those throughout. We know based on our model that A equals 1.04 and D equals 75. And now let's see how we can fill in our P sub n column. We know when n equals 0, P naught, we start with 0 individuals on the moon. Our initial condition, P naught equals 0. For each subsequent n, we are going to iterate our model, which is P sub n equals 1.04 times P sub n minus 1, the time period before, which in this case is P naught, plus D, 75. This would be our value for P sub 1, and it makes sense that after 1 year we would have 75 individuals that just landed on the moon, colonizing the moon. We want to be able to use this equation for all subsequent values of n. And so what we want to do is we want to absolute reference our parameters, which don't change from time period to time period. And we can either use the F4 key to do this or add $signs around those values for the parameters. So you can see here our new equation that locks in that value for our parameter A and locks in that value from our parameter D. And then we're able to use this equation for all values of n. And we find that when n equals 20, we have a P sub n which equals 2,233.356. So our mathematical solution for P sub 20 is 2,233.356. But we need to interpret this number, bring it back into the context of the real world. And in doing so, we can round and we can see that there are 2,233 colonists on the moon after 20 years. But that's only one step, or one part of the interpret step of the USMA mathematical modeling process. Let's go revisit our assumptions, and based on those assumptions, see if those assumptions changed what would happen to our model. So let's look at these assumptions. These were the assumptions that were initially made in during the transform step. When we conduct this sensitivity analysis, if we changed our assumption that there were no medical advances in technology that would change the birth and the death rates on the moon, what if we didn't know about lunar living? And what if the death rate wasn't quite 1%, but it was closer to 0? And those colonists living on the moon extended their life. So if we made a different assumption, we'd still have a birth rate of 5%, but we're going to make an assumption that the death rate is closer to 0%. And we see that that truly is a change in our model, because now we have 1.05 times p sub n minus 1 plus 75, and that equals our p sub n value. We could go back and see if this change in our assumption, which led to a change in our model, actually changes our results. And so we can go back to Microsoft Excel, change our A value, and see that in fact there is a change in the mathematical solution. And when we do that, we find that p sub 20 equals 2,479.947. But let's interpret this. And in the context of the problem, what does that mean? That can mean there are 2,480 colonists on the moon after 20 years. Or does that mean that there are 2,479 colonists on the moon? Think about the difference between rounding up and rounding down in this case. Are both appropriate? We can also compare this number to the number we found when we had a death rate of 1%. As compared to 2,233, this is an increase of 246 colonists. Is this significant? Did this change in our assumption change truly the mathematical solution and our interpretation of what this means for the real world? Well, an increase of 246 colonists on the moon, is that an additional consideration that we would have to make to house, to clothe, and to feed those colonists living on the moon? An increase in 246 colonists over the course of 20 years could be significant. And that's why we went through this iterative process. We conducted a small sensitivity analysis to see if the change in one assumption, changing the death rate from 1% to 0%, truly changed our overall solution. Thanks for watching, and happy modeling.